Weekly Robot News. Hello viewers, welcome back to your one-stop shop for all news robotics. We're back once more with the latest, sometimes shocking happenings of the robotic tech world. From robotic bugs that can go just about anywhere and robots helping with our healthcare, all the way to robotics being facilitated by augmented reality. Robots that actually convey emotions, and even shape-shifting robots. We have it all. So, without further ado, let's jump right into our weekly updates. However, before we do, we request you to subscribe to our channel and press the bell icon to never miss another upload of ours. Having said that, let's get right to it. Highlights of the week. Real robot bugs that go anywhere. These ancient creatures can squeeze through the tiniest cracks, fit snugly into tight spaces, and survive in harsh environments. There aren't many spaces that are off limits to an insect. Now, can you imagine a robotic bug that will do as you say? Well, that's exactly why researchers at the University of Pittsburgh have created tiny bug-inspired robots that can carry out tasks in hard-to-reach spaces and inhospitable environments. These robots could be used to access confined areas for imaging or environmental evaluation, take water samples, or perform structural evaluations, said Junfeng Gao, who led the work as a PhD student in industrial engineering at the Swanson School of Engineering. Anywhere you want to access confined places, where a bug could go but a person could not, these machines could be useful. For many creatures under a certain size, like trapjaw ants, mantis shrimp, and fleas, jumping across a surface is more energy efficient than crawling. Those impulsive movements were replicated in the robots, which are made of a polymeric artificial muscle. The robots latch on to build up energy and then release it in an impulsive burst to spring forward, explained M. Ravi Shankar, professor of industrial engineering at Pitt, whose lab led the research. Usually, actuation in the artificial muscles we work with is fairly slow. We were drawn to the question, how do we take this artificial muscle and use it to generate a jumping actuation rather than slow actuation? The answer lay in the interplay of molecular order and geometry. The curved composite shape of the polymer muscle allows it to build energy when it is powered. The way the molecules are aligned in the muscle draws inspiration from the natural world, where their combined actuation builds energy into the structure, said Mohsen Tabrizi, co-author of the study and PhD student in industrial engineering at the Swanson School. This is accomplished using no more than a few volts of electricity. Harnessing robotics to treat spinal cord injuries. Ever imagine what the world of healthcare would be like if doctors could have the precision of robots? Well, by employing artificial intelligence and robotics to formulate therapeutic proteins, a team led by Rutgers researchers has successfully stabilized an enzyme able to degrade scar tissue resulting from spinal cord injuries and promote tissue regeneration. The study, recently published in Advanced Healthcare Materials, details the team's groundbreaking stabilization of the enzyme chondroitinase ABC, offering new hope for patients coping with spinal cord injuries. This study represents one of the first times artificial intelligence and robotics have been used to formulate highly sensitive therapeutic proteins and extend their activity by such a large amount. It's a major scientific achievement, said Adam Gormley, the project's principal investigator and an assistant professor of biomedical engineering at Rutgers School of Engineering, SOE, at Rutgers University, New Brunswick. Robotic arm twisted into shape through augmented reality. Now, this is another interesting development. The flexible arm, which was designed and created at Imperial College London, can twist and turn in all directions, making it readily customizable for potential applications in manufacturing, spacecraft maintenance, and even injury rehabilitation. Instead of being constrained by rigid limbs and firm joints, the versatile arm is readily bendable into a wide variety of shapes. In practice, people working alongside the robot would manually bend the arm into the precise shape needed for each task, a level of flexibility made possible by the slippery layers of mylar sheets inside, which slide over one another and can lock into place. However, configuring the robot into specific shapes without guidance has proven to be difficult for users. To enhance the robot's user-friendliness, researchers at Imperial's REDS, or Robotic Manipulation, Engineering Degree and Science Lab, have designed a system for users to see in AR how to configure their robot. Wearing mixed reality smart glasses and through motion tracking cameras, users see templates and designs in front of them superimposed onto their real-world environment. They then adjust the robotic arm until it matches the template, which turns green on successful configuration so that the robot can be locked into place. Robot seems to convey emotion. Precision, effectiveness, and efficiency are understandable, but expecting emotions from robots? That blows our mind. Scientists from the Faculty of Engineering, Information and Systems at the University of Tsukuba devised a text message mediation robot that can help users control their anger when receiving upsetting news. This device may help improve social interactions as we move towards a world with increasingly digital communications. While a quick text message apology is a fast and easy way for friends to let us know they're going to be late for a planned meetup, it is often missing the human element that would accompany an explanation face-to-face or even over the phone. It is likely to be more upsetting when we are not able to perceive the emotional weight behind our friend's regret at making us wait. Now, researchers at the University of Tsukuba have built a handheld robot they called Omoi, which was equipped with a movable weight actuated by mechanical components inside its body. By shifting the internal weight, the robot could express simulated emotions. The robot was deployed as a mediator for reading text messages. A text with unwelcome or frustrating news could be followed by an exhortation by Omoi to not get upset, or even sympathy for the user. With the medium of written digital communication, the lack of social feedback redirects focus from the sender and onto the content of the message itself, author Professor Fumihide Tanaka says. The mediator robot was designed so that it can suppress the user's anger and other negative interpersonal motivations, such as thoughts of revenge, and instead fostered forgiveness. Next generation robots, Shapeshifters. Any Marvel fans here? Yes, we're talking Shapeshifters. Physicists have discovered a new way to coat soft robots in materials that allow them to move and function in a more purposeful way. The research, led by the UK's University of Bath, is described today in Science Advances. Authors of the study believe their breakthrough modeling on active matter could mark a turning point in the design of robots. With further development of the concept, it may be possible to determine the shape, movement, and behavior of a soft solid not by its natural elasticity, but by human-controlled activity on its surface. The surface of an ordinary soft material always shrinks into a sphere. Think of the way water beads into droplets. The beading occurs because the surface of liquids and other small material naturally contracts into the smallest surface area possible, i.e., a sphere. But active matter can be designed to work against this tendency. An example of this in action would be a rubber ball that's wrapped in a layer of nanorobots, where the robots are programmed to work in unison to distort the ball into a new, predetermined shape, say a star. It is hoped that active matter will lead to a new generation of machines whose function will come from the bottom up. So, instead of being governed by a central controller, the way today's robotic arms are controlled in factories, these new machines would be made from many individual active units that cooperate to determine the machine's movement and function. This is akin to the workings of our own biological tissues, such as the fibers in heart muscle. Geographic hints help a simple robot navigate for kilometers. The way most robots navigate is very different from the way most humans navigate. Robots are happiest when they have total environmental understanding, with some sort of full geometric reconstruction of everything around them, plus exact knowledge of their own position and orientation. LiDARs, pre-existing maps, powerful computers, and even a motion capture system if you can afford it, the demands of autonomous robots never end. Obviously, this stuff doesn't scale all that well. With that in mind, Dhruv Shah and Professor Sergey Levine at the University of California, Berkeley, are working on a different approach. Their take on robotic navigation does away with the high-end, power-hungry components. What suffices for their navigation technique are a monocular camera, some neural networks, a basic GPS system, and some simple hints in the form of a very basic, human-readable overhead map. Such hints may not sound all that impactful, but they enable a very simple robot to efficiently and intelligently travel through unfamiliar environments to reach far-off destinations. With that, we end today's dose of our weekly updates. Join in next time for more of such exciting news happenings from the robotic world.